Good evening, everyone. It's so nice to see you all here. The last time we had a Farrand lecture was in February of 2020. And it was the last, one of the last public events that the museum had before the pandemic. So this is a very special occasion. My name's Amy Harris. I'm director of the Museum of Natural History. And it's just great to be here with all of you tonight for the Farrand lecture. Welcome also to our live stream audience. This is a new feature for the museum that is actually a benefit from the pandemic. For those of you who are wondering, this lecture will be recorded, and we will make the recording available kind of mid-December. It'll go out with our Museum at Home email blast, and then it'll be posted on our website. I'd like to acknowledge that the University of Michigan is located on the territory of the Anishinaabe people. In 1817, the Ojibwe, Odawa, and Potawatomi nations made the largest single land transfer to the University of Michigan, seated in the treaty at the foot of the rapids. We acknowledge the history of Native displacement that allowed the University of Michigan to be founded. Today, we reaffirm the contemporary and ancestral Anishinaabe ties to the land and their profound contributions to this institution. The Museum of Natural History acknowledges the complicated history of settler colonialism and recognizes Indigenous sovereignty, the ongoing effects of colonization, and the global struggle for self-determination of Indigenous communities. Tonight we're here for the Farrand Memorial Lecture. Since it was established in the year 2000, a wide variety of topics have been covered, and you can see those listed in the inside cover of your program. The Farrand Lecture is supported by an endowment fund that was established by many, many donors, and they're listed on the back cover of your program. Many of you are here tonight. Thank you so much for your support. And we're still accepting donations for the Farrand Lecture, so if you'd like to be listed on the program, you can join everybody else. The Farrand Memorial Lecture was established in honor of William R. Farrand. He was professor of geological sciences and director of the then Exhibit Museum from 1993 to 2000. Sadly, Bill passed away in 2011, and the lecture became a memorial lecture. Tonight, we're very happy to have many members of Bill's family with us. And, it's just great to see everybody, so welcome. After the lecture, there will be time for questions. We're welcoming questions from both the live audience here tonight and those who are on the live stream. This year, we would like to also offer the option for audience members to submit written questions if they would rather not speak out loud. You can take an index card and pencil now by raising your hand, and one of our student helpers will run to you and give you a card. And they'll also be available after the lecture. During the Q&A session, please raise your hand to ask a question or hand your index card to the mic runner, and they will read it for you. And please speak into the microphone if you're going to ask a question so we can make sure everyone can hear, as well as the people on the live stream. For those who are watching the live stream, there is a Google form linked below the live video. So just click on the link and you can use the form to submit your questions for Dan Fisher. We have a staff member monitoring the Google form and, for responses, and we will try to balance questions from both our live and our remote audiences. And before we proceed with our program, I want to ask everyone to please silence your cell phones. And now I'd like to introduce Catherine Badgley, who will introduce tonight's speaker. Catherine is a longtime friend of the museum. We're really grateful to have her with us tonight. She is currently both the director and a professor in the residential college. She's also professor of ecology and evolutionary biology, professor of earth and environmental sciences, and a research scientist in the Museum of Paleontology. All of these roles are within the College of Literature, Science, and the Arts as is the Museum of Natural History. Catherine, thank you so much for introducing our speaker.
Thank you, Amy. Well, what a treat this is, and also an honor to introduce my longtime friend, Dan. And I want to start out with a story that will eventually lead to Dan. I was in the Michigan Theater a few years ago, waiting for a movie to begin, and I was in the screening room, which is small, probably as much less capacity than we see here. And it was a popular movie, something like Knives Out, and everybody was kind of packed in there together. And I was overhearing a conversation from the person next to me, who was a complete stranger, and it sounded interesting. She was talking something about growing crops sustainably, and I live on a farm, and I'm interested in sustainable agriculture as well as paleontology. So I introduced myself, and I said, what you're working on sounds interesting. And we started chatting, and I told her, by way of introduction, that I live on a farm and that I'm a paleontologist. And suddenly she got this really strange look on her face, and she said, "By any chance, did you compost an elephant?" And that's an odd thing to ask somebody that you've only met 5 minutes ago. But even more odd is the fact that the answer is yes. And that's where Dan comes in. Dan had been studying the living elephants at the Toledo Zoo, partly to investigate how elephants make trackways, like what you see in this picture here. And the folks at the Toledo Zoo knew of his interest in behavior and anatomy, and Dan had expressed an interest in getting a skeleton if ever an elephant died of natural causes. Well, as it so happened, an Indian elephant had died, I think it was 17 years earlier, and had been buried 27 feet under the ground in the landfill of Toledo, of the city of Toledo, and long, not exactly forgotten, but buried and out of sight. And the landfill was growing in capacity and started to excavate the area where the elephant and other large mammal carcasses were buried. So Dan got a phone call one day saying, "We have an elephant that needs to come up today, and it's going to go into a dump truck. Do you want it?" And Dan, of course, wanted it, but he had to figure out where he was going to put it. So he called my husband, Jerry Smith, and said, "Can I bring an elephant carcass over to your farm today?" And Jerry said yes, without asking me, knowing that I would have given the same answer, which was correct. So I learned about this later in the day, and we got home, and there was this enormous carcass sitting on our lawn. And Dan was there with a couple of his students, and with big buckets, and they proceeded to we proceeded to plan what we would do with that elephant carcass. And the short version of what happened next was that the neighbors came down with a giant tractor, pulled it over to our compost pile, and then a farmer neighbor down the road brought a huge load of composted manure and covered the carcass with it, partly so that we wouldn't get the effect of the smell, which was very curious. It wasn't a putrefying smell at all. It was almost like a strange, very penetrating rancid smell, because it was, anyway, the compost covered it, and the bacteria in the compost did the job, but it took several years. And now the bones are all here. In any event, this is an example of Dan's wide-ranging approach to study of the fossil record. Dan has been a curator in the Museum of Paleontology and a professor in the Department of Earth and Environmental Sciences for over 40 years here. And he's a cherished teacher and mentor. I know that from experience sitting in on some of his classes, and certainly in hearing many of his lectures, and knowing many of his students very well over the years. Dan is an exceptional scientist for the originality of his ideas and thoughtful ways to test them. And I just want to mention several themes that he's taken up over the years. One is, like, as the elephant carcass manifests, one is using knowledge of living species to inform the study of extinct species, and that's many paleontologists do that. He's also developed a number of insights about evolutionary processes from studying changes in form and function of fossils over deep time. And he devised a method for reconciling the gaps in the fossil record with the construction of evolutionary trees that include fossil data. And with the work he's done on mammoths and mastodons, which you'll hear about tonight, he is testing ideas about the role of Paleo-Indian societies in causing the extinction of these remarkable animals. So I'm going to turn it over to Dan to tell his stories now. And please help me welcome Dan Fisher.
I counted among one of the very great matters of fortune to have friends as good as Jerry Smith and Catherine Badgley. I doubt that many of you would have a place to put a stinky elephant that Toledo demanded be removed from their city limits before nightfall. It's a complicated story, but not one that we have time for right now. I have my own challenge. And although this is a story that actually will not include much of the human role, possible role, I should say, I guess, in the extinction of mammoths and mastodons, I hear something on sound. I think we turned the lavalier on. We need to turn it up. It's in my back pocket. It's on. Now that worked. Okay, you must have done it. All right, thank you, Steve. I will mention only briefly and only in passing that humans may have been involved in the extinction, but those are open questions, and it would take even more than a whole evening to really discuss that. What I'd like to talk about for you this evening is really this animal that you're looking at here. The Buesching mastodon is what it's called. Buesching is a family surname. I'll introduce you shortly to at least one of the Bueschings and say a little bit more about this animal. But first, I just want to make the statement that we as individuals who can come and visit this museum, we as an institution are really profoundly fortunate to have a specimen like this in our collections, available both for study and learning from. Many more people walk by it than really know what lessons it has to tell us. But I'll try this evening to give you at least a little bit of insight into really some of the unique things we've learned about the biology of these animals from studying this individual. Now, what you see out there, of course, and what you see in this picture is not the original specimen. For that, you need to go to Indianapolis, to the Indiana State Museum. That's where the specimen was donated. But it was donated to a formal museum institution, and that's a critical step in the preservation of the information and the value, really, of specimens like this. All such specimens, certainly all that start out on private property, are initially, the way U.S. law goes, property of the landowner. And it's their choice what will happen with them. Sometimes they get sold. Sometimes they've been promised for study and then get sold out from under us. But this and quite a number of other specimens are wonderful examples of a public-private partnership when individuals agree to donate specimens and allow them to be studied by people who can devote the time, energy, and if necessary, funding to do what needs to be done in order to learn everything we can from these things. Now, as I said, the specimens in Indianapolis, this is a cast, a very good cast. I mean, it's absolutely professional quality and finished off in a professional manner. Moreover, there's more thought that's gone into the mounting of this individual, or proper representation of anatomy and so forth than I think can be said of almost any other mastodon mount. Again, I won't be able to say much about that because I got to get rolling on this story. We will come back to the small matter of what this mastodon appears to be standing on. That's certainly an interesting part of the story. But for right now, I need to acknowledge the paper that really represents the occasion for bringing us all together to talk about this tonight. This is a paper that a group of colleagues and I published in the Proceedings of the U.S. National Academy of Sciences just this past summer. And this is the first page of the PDF of that paper. People typically do such things somewhere in such a talk, I guess, to sort of make it clear that, yeah, it got published, it got by peer review. Granted, there were times when we wondered, but it did. Now, I don't expect you to be able to really read anything much from this image, so I'll just put up here in larger font at least the names and affiliations of the co-authors. Josh Miller is my joint corresponding author. He's in the Department of Geology at the University of Cincinnati. And you'll see, looking down the list, that really a lot of these folks are either geologists or paleontologists or anthropologists. We all work on things where the boundaries are quite thin. The problems really stretch across fields. And so there's a lot of interdisciplinary work going on. There is also, certainly in Alex Konomi down here, a mathematician, a statistician. And he's had a major role, along with Josh Miller, in developing here's a phrase for you, the hidden Markov model that is going to be used for some of the inference of patterns of landscape use from some of the data that we'll be gathering from this mastodon. Another person, well, two other people I feel obliged to say something about. Brooke Crowley is not someone whom I've really known for very long herself, but she is a student of one of my first students here at the University of Michigan, Paul Koch. And I know some of you know Paul and his very impressive career for many years now. Another alum is Ross Secord, who's now at the University of Nebraska-Lincoln. And Ross stepped in at a really critical moment when we needed to do analyses of oxygen isotope compositions from the mineral phosphate in samples of this mastodon's tusk, and I'll lay the groundwork for that. But my point is that you've got people that are really experienced here, that each offer some distinctive contributions that we couldn't have done the project without their work, as well as people who sort of interleave and conjoin many of the issues that arise in this sort of study. Now, the title is I think a pretty simple declarative statement, and I've basically rewritten it here as the first of a series of three main points that I want to introduce you to. What is this paper about? Here's the bottom line on it. Here's what it claims. The first is that there was a change in landscape use by this individual, presumably members of the species, as they matured. Maturation, what do we mean there? Most of us know by now. But in this case, we're talking about that transition basically starts with puberty, goes through adolescence, on into full adulthood. It's a little bit more complicated in elephants, but we'll get to those details as we get along. What's another main point? Well, it turns out that mastodon, at least for adult males, landscape use changed with the seasons. Summer is different from winter, it's different from, autumn and spring. Well, that's interesting, I guess. It also turns out that we argue that adult male mastodons migrated seasonally to find mates. The first thing I want you to do is I want to encourage a sense of healthy skepticism here. Where are these guys coming from? What time machine did they just step out of? How could we know anything about how animals in the past moved across their landscapes during their lives. And that's, on the scale of tens of years, even multiple decades. But just change it to the scale of seasonal changes. How do we know what they did at different seasons? How could we ever know that? And in particular, how do we presume to know the reasons why animals of the past traveled from one place to another? You've got to have some trick up your sleeve. Well, to give you just a couple hints, or at least directions in which you might think, how would landscape use be recorded as animals mature? So think about what part of their anatomy you're going to look at to learn about this. How would landscape use be recorded in a seasonal fashion so that you have information on what they did at different seasons? But this one has got to stump everybody. How can data on movement and mating activity and time all be retrieved from the carcass of a single animal? It just seems almost magical. Well, it's not magic, it's science. Now, you've all been to the East Atrium, and you've seen the Owasso Mastodon, which is our adult female right here. I admit this is not maybe her best angle, but you get my point. And this is the Buesching Mastodon from a similar distance and direction. And the reason I've chosen this particular image is that it also shows to pretty good advantage the trackway that they're standing on, the set of footprints. That's what you're looking at here. You may not have known it. To be more precise, it's a fiberglass cast from a fiberglass field mold of an actual set of mastodon footprints that we excavated at one of our sites. And you might look at that and say, I don't know, it just looks like some, giant, let's just say, giant in puffy slippers, walk down, and I see a sort of bipedal sequence of footprints. Well, it may look that way, but that's obviously not very consistent with the setup here in this exhibit. It certainly implied that this is the trackway of a mastodon, and indeed it is a trackway formed by a quadrupedal animal. That's not a bipedal trackway that you see, and I'll tell you more about how we know that. The real key is that even though trackways as a single structure are in some sense a static structure, they tell a story. There is a progression in time because they are made up of components that were produced serially in time. And if you know the process that's represented by that series of prints, you can decode some of the details of how the trackway was made. In other words, there is a dynamic process walking at work, and we just need to know more about how elephants walk in order to interpret this trackway. Now, this is just a quick shot to indicate something of how the trackway was preserved. It was preserved at the interface between two contrasting types of sediment. Below was a stiff, dense, sandy clay unit. Above was a soft, fairly light marl, a carbonate unit. Really strong contrasting properties. And it was possible with careful troweling to just cut down gently to that interface and lift away the overlying marl, much like you'd lift a butter pat off a saucer. And it was by doing work like that, here it's being shown by John Farmer, one of our volunteers from the Michigan Archaeological Society, who helped recover much of this trackway and work at this site. We should say that we also had volunteers from the Friends of the University of Michigan Museum of Paleontology, and indeed other volunteers all around. And I'm going to try as I go to give a nod to as many of those as I can, but just be aware that there are many tens of people, hundreds of people who have helped over the course of all of this work. There's more that can be said here, but I know I've already shifted into a lower gear than I need to be in. This is a shot just looking down the whole trackway just before we made the fiberglass mold of it. This is a 2-meter long folding rule, and the white lines across the sort of paralleling the trackway are nylon ropes that we used as sort of the margins, the sort of soft margins of the fiberglass layer that we poured and produced to capture the details of that surface. It's a long story, but basically we lifted that up and carted it home. I took out a bunch of slides to make this a little shorter, and now I need to take advantage of that. So that's a mastodon trackway. It is important, though, to come back to the Toledo Zoo, as Catherine mentioned. It was really only by watching elephants walk and documenting the way they walk that I was able to fully understand what I was looking at in the trackway on site. You have a sequence here of footsteps. Forget about Don Red Fox stray print here. He was the elephant manager at that point at the Toledo Zoo. Very helpful. But he guided one of their more cooperative elephants on a slow walk. We tried to keep the speed about the same, but as it, I guess it doesn't say, well, it says a little bit here. I think that got cut. There's a slight change in speed along this trackway on the left. There's also a change in the trajectory of the trackway, you'll notice. But the difference between these two, aside from this one being slow and this one being fast, is that in a slow walk, and of course it's a slow walk of a particular speed, the hind feet, once the forefoot is lifted up, the hind feet come and are set down almost exactly where the forefoot was. And so the prints go into almost perfect registration. And, left limbs do it, right limbs do it. And so what looked like that bipedal series is actually pairs of footprints, one four, which the footprints are more round. You can see that in the legend down here. The hind footprints are more oval. The hind feet step onto the forefoot prints in a slow pattern of movement, as long as the animal's going on a direct trajectory. If it begins to veer one way or another, they come out of registration. If it's a fast walk, in fact, the hind footprints actually step beyond the forefeet footprints. And that's what you see here on the right. And what we saw on that trackway was clearly what we see on the left. So it's a mastodon in a slow walk. Turns out he's also walking in about 1 meter of water. And there are a lot of other details, but the point is, know the process, read the phenomenon, understand how it works. And it's basically the key to solving those other problems I said at the beginning. How are we going to answer those questions about this animal's life history and its landscape use? Now, I have to get on with the Buesching Mastodon. Buesching Mastodon was found by the Buesching family, who run Buesching's peat moss and mulch outside of Fort Wayne, Indiana. And this is Dan Buesching down in the picture there on your lower left. He was operating the hydraulic excavator, carefully digging out marl, separating it, digging out peat, separating it. You know, it's a landscaping operation, lots to do. There was this thing, though, that resisted his shovel. He eventually got under it and pulled it out, thought it may be a tree stump or something. But as he began to clean it off, it turned out it was the skull of this animal. And shortly thereafter, bone after bone after bone. But he didn't let all of that play out before he called someone. And in fact, he gave very prompt notice of what was happening. The local university, which at the time was called IPFW, Indiana, Purdue at Fort Wayne, called me up, and we arranged to go down and help at the site. Here, Dan Buesching is holding the left femur of that mastodon, so you can see it's a size. I mean, he's a sizable guy. That's a sizable bone. You see Fort Wayne. The map here is, of course, a sampling of mastodons from North America. There are thousands of mastodons in North America, not unusual in that sense. But here on the right is a list of sort of footnotes about the Buesching mastodon, And since I'm going so slowly, I think I better let you read that or come back to it, please. And here's a lot of the things I've said, some I haven't, but I think the things I do want to make are right here, the points I do want to make are right here at the bottom. One of the really distinctive features of this animal is that it became the star specimen for our University of Michigan online repository of fossils bone picker application, which I'm sure many of you use on a daily basis, right? For all your questions about mastodon osteology. My friend, former student, staff member here, Adam Roundtree in the back row there, is our 3D wizard. And he's the one who basically set up this online repository. And the bone picker allows you to, I'll have just a quick shot of it a little later on, not very later on. I'll just proceed here. There's this landing page of at least an earlier version of the site. This is the URL. It's not a live link, but copy that into your browser, and you can go and see this icon, click on it, and open up a screen with the Buesching mastodon looking at you. You can mouse over it and turn him this way and that. And as you mouse over a bone, it will light up and tell you what bone it is. And moreover, if you double click on it, it'll open a separate window where you have a 3D model, texture mapped, looks like the real bone, that you can twirl this way and that, and study it to your heart's delight if you want to really understand the anatomy of that bone. Sorry we can't do that here in this talk. Just to give you the sense of that, here is a digital model of the articulated animal doing a sort of, runway spin for you. And we'll carry on. So we were at the site. We don't do this halfway. We're a family. Our kids have gone to mastodon sites since their first weeks of life. Wife was nursing each of them for more than a few days when they were little, very early in their lives, and they sort of grew up digging and playing and talking to the volunteers and things like that. So it was no big deal for them to be there at the site and standing in for scale in Dad's photo of a part of the exposures. In case you were wondering about the party work that you see these red streamers here, actually this is me. I'm standing holding the reflector, the sort of target unit of a total station, a sort of laser survey unit to actually collect coordinates for individual elements. And so you put that staff here and there and there, and you end up collecting coordinates, 3D coordinates for a set of points that show you exactly where that tusk was in the site. And we did our best to measure in every bone that was there. What's of interest here is that both tusks were sitting there side by side, sort of spooned with one another, points together, basal ends together. And here you can see at least the one that was lowest in the site a little better when more of the sediment and the other tusks get cleared away. But that's what this looked like. These were very well preserved. Okay. Again, I'm going to fight this battle of time all the way, I guess. I had an animation that showed you the growth of this idealized model tusk. I cut out the animation. I'll just talk about the last frame of it. What you see here is what you would get if you had cones, let's say colored cones, had a color cycle that represented each, let's say, month of a year with a different color, and let that go through its sequence for the first year, the second, the third, and each cycle of the rainbow sequence is in another year of life, and you keep adding cones to the inner growing basal end of the tusk here, and you see how the tusk grew. Now, this isn't a perfect model. It doesn't represent the cementum, which is a tissue that forms on the outside of tooth roots. By the way, tusks are teeth. It's basically an incisor tooth. What we're not seeing in the cementum here, that would be a thin layer on the outside, nor are we seeing any representation of breakage or abrasion that takes place during the life of the animal and that alters the appearance of the outside form. But this is the basic geometry, and so you should start thinking about what that geometry would look like if it was broken or abraded or processed in the lab in a certain way, which we'll be doing. Okay, another couple structure diagrams here. This is what such a structure would look like if you cut it longitudinally. And if there's any problem with this, it's just that the pulp cavity is not quite long enough and it doesn't show you the very low angle oblique nature of these cones within cones within cones. They're really quite elongate, and so it's a structure that's structurally sound, resists bending and so forth. It looks different, of course, if you cut it transversely than if you cut it longitudinally. And if you begin to look at this at the fine structure, it becomes clear that these larger units, which we know by arguments that I'll suggest in a moment to be years, inside of those are still finer scale layers that, in the case of mammoths, represent both weeks and months, weeks and days. In the case of mastodons, represent fortnights, or sets of 2 weeks, and the days expected within a fortnight. Automatically bump to the advance. I guess it's cueing me to go on. This is a thin section showing you a mastodon, some mastodon dentin, and these actually are the daily increments that you see right here, these dark light couplets. And you can see that every so often there's some that are darker. Sometimes there's a darker one that slips in there, but there's at least an extra darkening that occurs every 14 days in this case. And these sequences of tusk layers end up being really diaries, literally, of the animals' lives. And they tell us a lot about their rates of growth, and it turns out many other things about their lives. So how do we study this? Well, we have to, break eggs to make an omelet, as they say. We have to cut tusks to learn about what's inside of them. There are things you can learn from the outside, but a lot requires that you get inside the tusk for reasons that I think will become clear. This is the right tusk of the Buesching mastodon back in the lab, and here halfway along on the bandsaw, it's being held up by a rolling scaffold that I fabricated from, plumbing supplies, and it allows me to just sort of centimeter by centimeter roll the specimen along as the saw blade. It's a low speed saw with its got direct drive, so it's able to very carefully and slowly cut and it's got a carbide teeth on it, very slowly cuts its way all along the tusk. Now, that only opens the book. It only gives you access visually to what we're going to do. But the next step is to make a second cut parallel to the first, removing just about a 1 centimeter slice. It's a whole lot harder to do that a second time than to do it even once. In the old way, cutting freehand, I did do it. It wasn't a perfect cut. There were other problems. Again, that's another story for another day. But here's how we do this more today, using what I call a rocker box. Basically just like the rockers on a rocking chair, but all situated around a box where you can use polyurethane foam to stabilize a specimen within the box. The rockers then control much of the attitude, and you can just tip it as you want and feed it through the saw. So this is an elephant tusk with the first cut being made starting at the tip, and you cut just to one side of the axis. Now, here we get 2 more shots. This is getting into the second cut. In other words, the first half has been set aside. That was right here. And now we're making a second cut just a centimeter off from the first, and we're going to go to the other end. Here we are coming out the other end, so the thing that's reversed sides, you're looking at it from the opposite direction. And here we're just finishing that cut. And then here I've taken the cut, and you have my poker face on there, not to give away whether it worked or it didn't work. but the answer is it worked. And in fact, there's a quite nice centimeter thick slab there that will let us do all the sampling we ever need to do to study any part of the life of that animal and still have the other almost halves, untouched and available for display or whatever. So that's some of how we work. So what do we do with all this? Tusk analysis is based on things we see, we observe, and things that we infer. What we observe, basically, there's structural features, there's a variety of them, and compositional features. And the data that we get are about the animals and about their environment. And here are some color patterns that link up sort of what gives what. Both measurements of the thickness of annual increments and their length on the outer surface of the tusk yield information on the sex of the animal and its age of maturation. I'll show you how you get that. Oxygen isotopes, and we used oxygen isotopes from the phosphate component of the mineral hydroxylapatite, which is the mineral component of bones and teeth and certainly tusks. And that gave us information on the age, to an extent health status, but the season of death, and in fact the seasons of every bit of record of the animal's life that was preserved in that tusk. And finally, strontium isotopes were used as a proxy for figuring out where on the landscape the animal was at a given point in its life. And so it's from that we get information on migration. Now, you haven't yet seen a close-up surface picture of this particular tusk. Here is a shot. This is sort of not too far from the tip, not halfway along the tusk. You see these sort of loopy patterns here, and the dark lines, the lighter patches, and so forth. This is a winter-spring boundary right here. And just downstream from it, that's then the first spring growth that followed that winter-spring boundary. And then here is summer, here is the next fall and winter in all these lines, and here's the next winter-spring boundary about here. At the time I numbered this boundary, I put this number on here thinking it was the beginning of year 5, and this the beginning of year 6. It's actually the end of year 5 and the end of year 6. Up here you see a piece of cementum, but here the cementum is all worn away. Here's some more cementum. I want to sort of make a link now between that photograph and this drawing. In fact, here's where we're looking at there. And this year 5, my 5 number was right there, but I hadn't yet seen the 1 here. It turns out the first year in the tusk is represented only by a little patch on the top of the point of the tusk, and that added a year to those I needed to count, and so that's why the numbers shifted by 1. So I'm showing you the process. You learn things change. Overall, we're looking here at sort of from underneath and toward the midline of the animal, given the sort of curvy pattern of the tusk there, and we can trace years 1 through 16 easily on this abraded surface that we're looking at here. That's where the dark colored material you see is the cementum. That's all been worn away from the underside. Why is it that that so much of the cementum is worn away? One of the things the animals do with their tusks is strip bark from trees and ingest that and stick a tusk in between the bark and the tree and whip it up and down a few times, and you'll abrade a lot of cementum off of that, both sides. Dig a few holes for water, and you'll abrade even more off the underside. And that's why so much of this is free of cementum on the underside of the tusk. It's only as you get toward the middle that you get back to some tusk that's covered by cementum. And here's the basal part of the tusk. Here now you do have cementum all over these surfaces. There are features here, topographic features, that we're treating as marking years. There's a term for them. They're called periradicular features. That is, they go around the root. We're looking here at the root of the tusk, like a root of any tooth. And I don't want to say too much more about how those form. They're complicated. or why exactly yet, though we will get to this, we consider them years. The other thing that I want to point out is that just on the proximal or sort of basalward side of these winter-spring boundaries, which is the solid lines, you'll see a whole bunch of dots here, these things that are called cementum defects. They're a very particular phenomenon that takes a little puzzling over. And there's basically one of those after every winter-spring boundary in this portion of the tusk, which is to say the last, 6, 7, 8 years of the animal's life. There is a year 32, that you don't see here because it's not preserved on any of what you see. You can only see it if you look at one of the cut surfaces on the other side. And likewise, these are years that you don't readily see here. I put them in brackets, but you can view all of them from the other side of the specimen. I really have to move. This is a diagram that sort of gives a sample of the animal's life. We don't show the first few years here. It starts at 5 and goes to 35. This scale reads mastodon age, and reviewers wanted us to talk about age, make age identifiable. So we did. But you have to understand that what we know going into the problem is not age per se, but just year in the tusk year, the first, the second, the third, whatever. And it's a separate matter to figure out how old the animal was for each of those years. So in fact, we did a comparative study of animals of this age and ones young and ones that were much younger, at years that were not preserved on our animal. And it was by making comparisons there that we learned that probably about 3 years had been broken or abraded from the tip of this tusk. And so only then did we convert tusk years to age, and you get that by tusk years. I guess it should say age minus 3 instead of, it should be plus 3 here. Made the slide in a hurry. Would give you mastodon age. Now, what's interesting here, though, is what's with all the up and down. The y-axis is measuring change in annual extension length, how much length is added to the tusk with each passing year. And we measure that for 1 year and measure it for the next. And when the line goes up, it means that the subsequent year added a lot more length than the previous year. When it goes down, it added much less. And it looks like what's here called year 12, or what in tusk years was year 9, was not a good year. And in fact, it even stands out. Some of these other places where the line goes down, you can tell it's for other reasons. It has to do with other details on abrasion and so forth. But there was quite a bad year right here. And this, in fact, is an age at which in virtually all mastodon males we see quite a bad year. And it turns out, I believe, that we're looking at the time in life when those young males are finally kicked out of their matriarchal family units and said, you better fly right or fly on your own. And the answer is fly on your own, because you're cutting up too much with your younger brothers and sisters. And so, although he has had sort of protected place of pride within the matriarchal unit for years, as he grew up, he's now being pushed out on his own. And he can spend as much as a year basically hollering and bellowing on the fringes, let me in, it's me, why hast thou forsaken me? Until finally he gives up and begins to address what's necessary to live in the world on your own. And the red features down here are basically data on ages of puberty for other male mastodons, a mean, standard deviation, and a range for about a dozen other individuals that we have. So in fact, this is really the same age at which this tends to happen. And I think that's what's going on. Now, there are other ways to test that, but let's move on. Our reading of the life history so far is that was puberty in full blast. This is the beginning of his adolescence, and it was then the next few years, which had some steps forward and some steps back. The next few years when he finally got going and making it on his own. And we're then going to pick up the story again only toward the end of his life. We'll have some access to information on these years in here, but our direct sampling of the tusk tissues, the dentin, is going to be limited to the last 4 years of life. We're going to study about 6 years from adolescence and about 4 years from the end of life. Okay, here is a diagram of that axial slab that I cut out of the tusk. It only went a little bit wonky, and it basically the cut sort of came out of the exactly proper plane at one point, but it was no big loss because what was I going to do with a great long thin thing anyway? They're going to need to be cut into pieces to be studied, and so here is about 2/3 of the tusk, and here's then the proximal third, and now you see what I mean by a really long acute pulp cavity. And if you imagine then the orientation of the ears in here, they're quite low angle. What that means is that although there's a lot of light, 32 years and plus represented here, we were able to assess about 1/3 of that, 10 years, by 2 small blocks. One cut from here that got tusk years 9 through 14 in optimal position to have them represented in their most informative way. And here, another 4 years, years 29 through 32, where we got the end of life, basically. Okay. These were those 2 blocks that we cut out, and these are the years that were sampled in those 2 blocks. And what you're seeing here are the mill path that we followed with a stationary dental drill with a diamond bit on it, and we looked through a microscope at that spinning bit and drove it down the road, so to speak, drove along those lines on the polished surface of the dentin that marked days and weeks and so forth. So I'll give you a sense of how that looks in a minute, but here this is the adolescent sample and the adult sample. This is just a piece of the proximal end of the tusk, the growing end of the tusk. And I wanted to point out a couple things here. This outer layer is the cementum. It's sort of a yellowish color. And note that there's a dark line just underneath that is the actual contact between dentin and cementum. And note that this has this little bloop. I'm going against time here. I should do it this way, this way, this way. Each one of those is one of these periradicular features. There's a process in the growth of the tusk that leads to this little jiggle, let's just say. Then cementum is formed on top of that. And if you look at this closely, you may or may not be able to see it from where you're sitting. As the cementum gets thicker and thicker, the topography gets smoother and smoother. It's like a blanket of snow covering that little topographic ridge, and it becomes less and less clear as more cementum is piled on. And that's why it's harder to see some of the year boundaries in the middle of the tusk than others. The crazy thing here, or what sort of looks a bit odd, seems like the numbers, here there's a reference to year 32, and yet the last tusk year that we see on this representation is year 31. What happened to year 32? Year 32, it turns out, broke off. How, why? Those are other questions, but get ready for some surprises like that. I want right now to go to the end of life. So this goes back to our mount of the Buesching Mastodon in the Ruthven Museum before it came over here to BSB. And we're going to go up and look close right under its cheekbone right here. And here's what we see. You're looking right here at its upper right third molar, so right there is wisdom tooth, and just above and behind that wisdom tooth is a hole. It's about 5 centimeters across, round hole. What makes that? Well, I'm going to argue it's a tusk tip. Somebody shoved a tusk tip into his head, not just into his head, but through the jaw closing muscles and through a lot of other anatomy. And here to a place, this canal right here, the allospheenoid canal, is where the external carotid passes on its way to giving blood to the brain. Tell me that's not going to be a problem if you smash through here and, oops, nick that carotid. And I think this is at least an element of what finally went very, very wrong with this animal and led to his death. There's more. There's evidence of other injuries and so forth. But this is a very injury that suggests a stereotypic mode of fighting that I'll now illustrate. I wanted to give you a closer up view of this. I think the point I wanted to make here was note how sharp the bone is here. It's not weathered, it's not fractured, it's not fallen apart. This hadn't sat out and been rained on and sunshine on it for a decade or anything like that. This is crisp, well-preserved bone. It got buried in the pond, in the peat, within probably days of the animal's death. And so this is a very fresh signature of some kind of injury. Now, I asked, do elephants do this? Yup, elephants do this. When do they do it? Well, males do it when they come into what in a cervid, a deer, some member of the deer family, you would consider the rut. In elephants, it's called must, and that's a Sanskrit word. It was first recognized in Asian elephants, but has now been very clear that it's the same phenomenon, same physiological basis, same behavioral syndrome in African elephants. And they will fight, sometimes to the death. And although these two are not at the moment puncturing either flesh or bone, they do that from time to time, and animals absolutely do in these battles. For mastodons, we have to be a little more imaginative, and so we took our digitized skeleton, including skulls of the Buesching mastodon, and I guess the way a little kid plays with toy soldiers and so forth, I got my computer out and my animation software and animated a little movie, if you will, that showed how I imagined they would fight. I wasn't trying to just play here. I was trying to actually see what would it take to put your head in the right position, to make the tusk go along the right trajectory, to actually punch the hole where it gets punched. And it's not quite in position just here yet at this second, but it will be in the next moment as the animal moves forward. And it's basically a strong sort of uppercut-like motion of one of these curved tusks to plunge into the opponent's cheek. And yes, it does a lot of damage. Okay, so that's how the Buesching mastodon died. And there was a lot leading up to that as well, which I sort of have given a nod to, and we'll come back to if we can. I think we'll be able to. Isotopes of oxygen. What do they have for us? What do they bring to us? They bring a lot. They bring us a large amount of data on climate, the environment. In fact, that's where our seasonal information is going to come from. Isotopes, as I hope most of you know, are alternative forms of a given element that have, for a series of isotopes, successively larger numbers of neutrons here. 8 protons and neutrons for oxygen 16, 17 has 9 neutrons, 18, 10. It's pretty standard stuff. It's the oxygen 16 that's the most common isotope. The others, which are much rarer, and when we measure isotopes, we're basically looking at ratios of the rare ones to the common ones that that are everywhere around. And what the isotope ratio is tells you things about the history of the water vapor that's led to a given precipitation event, the history, the hydrologic history perhaps of the stream or the lake or pond that may be the source of water for an animal for their drinking. And so you learn things about the time of year and the sort of climate that you're dealing with from measuring these isotope ratios in the animal's tissues, because it's picked up those isotope ratios and their appropriate abundances from the world in which it lives. Those who deal with this know this Del notation. I think enough of you are from other disciplines that you won't worry if we pass over most of that. But there are standard, it's basically ratios, and there are standard ways of talking about large numbers, large values in ratios. Now, what are we supposed to learn from this? This is a sort of a clock model of the year. It's a little small, but it's abbreviations of month names. And the color pattern you see is sweeping to the north and sweeping back to the south. The warm colors indicate warmer temperatures of condensation, of precipitation, and those show up in higher ratios of oxygen 18 to oxygen 16. And when it's cold, when it's cooler, when it's winter, you get lower values. And so you expect these values to go up and go down depending on what sort of climate you're dealing with and what sort of season you're dealing with. So let's move on. There we go. I'll just show you some mammoth tusk dentin. It could be mastodon, but what I picked this for is because I'd already sort of showed how we do serial sampling. You see the labels on the right here: week 1, week 2, week 3, week 4. I mean, literally, we can see weeks in the tusk, and we can go in and drill out some more sample and some more sample in a series of samples that give us each, an example of what was produced during that week of the animal's life. Now, we don't usually do week resolution. It's too much work, too much money. But in this study, we did a sample about every month and a half on average, sometimes as little as a month, sometimes as much as 2. But that's going on, 8 or so samples per year. And that's quite a bit of resolution for looking at this animal's environment. And here's what the data look like. That is, this is a graph of oxygen isotope values on the y-axis here, and sample position for the adolescent years and the adult years here. And what do you see? You see this very regular pattern of values going up and down. You say, I don't like graphs, I don't do math. Think of it as music. It's just, and it's summer when it goes up and it's winter when it goes down. And you can look at each of those samples and say, whoa, this formed during the summer. This one formed during the winter. And look how regular they are. Do you now, anybody want to argue that these are really years? Because there's no other process in nature that gives rise to these undulatory pattern in oxygen isotope ratios. And remember, these are phosphate oxygen that we're looking at, and that's particularly resistant to any sort of postmortem, alteration of values that can happen in geological settings. But these are solid data on time in this animal's life. Okay, now you notice there's some dashes across here. It's marking basically the middle of the range for that half year of the cycle. And the reason that's important is that we're going to calculate what are called z-score transformations for these values that show whether they're high, 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 or only sort of high, high within the year, or low, 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 or really sort of low. So larger positive numbers are going to be really warm season of the year. Larger negative numbers are going to be cold parts of the year. And now we shift to strontium isotopes. And there's a lot here. I got these slides from my colleague Josh Miller, and I had to sort of pack things in a bit. So forgive me, Josh, if it looks a little hard to absorb on first glance. It's clear that here are the two isotopes of strontium that we're dealing with. 87 to 86 is the ratio we're interested in. It's determined basically by local geology, by the age of the rocks and their composition. Let's move on, and I think this is the real key down here. We are interested in matching strontium isotope ratios that we read from the tusk material, from the tusk dentin, and then finding where on the landscape can we get that ratio of strontium isotope compositions. Here, there, oh, maybe over there. And we have to do the work to find out what the pattern of distribution is. This is just a geologic map. It's only there to tell you that there's a lot of variability in rock type across any large area like the continental US. If you look at these samples, it's important to know with what resolution you can measure these values and how well you can compare them. And you have to understand that the sample standard deviation, your ability, in other words, to reproduce a number from a sample, is about 0.000005. That's a really tiny number. You can make, very fine measurements if you need to. And what we're going to do, just to sort of account for a little slop in a lot of things in nature, is add on a still small. We're going to be targeting. We're going to be looking for compositions that are greater than or less than a target amount by this amount, 4 zeros, 0.75. So we're going to look for anywhere on the landscape where we can find things that are even close to what we have on our sample. And I'm going to move on here. It's basically bedrock and water and soils that give rise to, that make these strontium isotopes available to organisms. And then they get into plants, and to drinking water. So it's basically drinking and eating that gives the strontium isotope ratios to the animals, and they are then faithfully represented in composition of teeth and bones. This is a map of strontium isotope compositions across North America. You can see there's a lot of variation. Unfortunately, the area that we're really interested in, which is right here, there's not a lot of relief, a lot of green there. But if you look very closely, it's greens and yellows, and in fact, although, why don't we see these bright oranges and blues and things like that? Because that would be rocks that are way out on the scale in some other direction, a different kind of rock, get those strontium isotope ratios. The point is, even the little bit of variation that we have in our area and in our samples is enough to find where you can and where you cannot match that on the landscape. And that's what we're trying to do. Looking down, here's southern Michigan, Indiana, Ohio here. You can see the telltale thumbprint, if you will, of Lake Michigan. What are all these yellow speckles? The isoscape, the map of strontium isotope ratios has a resolution, an inherent resolution of about 1 kilometer. That's the size of the pixels that we're looking at. And so we're looking for pixels on our map that have values that match what we measured to within that fudge value that we allowed for. And we used something called a kernel density estimator to sort of statistically treat the data and sort of corral places that are in the right range of values. And we call these potential regions of occupancy, or PROs for an acronym here. And for this one sample, which is in year 32, this is the largest potential region of occupancy. This is its centroid. Here are other places that match, Now, could it have been there too? It's possible. The whole process of doing this analysis, I need to go on to the next slide, has a couple more steps. Any given set of pros from one sample, this is from the earliest sample in year 9, will often give you multiple regions where there's some degree of match. The brighter red here, that's where we have a probability of 1. We're bang on. That's a very high, very likely spot that the animal could have acquired that composition. These are places where you can get something close to that, where you could maybe find something that matched, but not such a good call. So which of these are you going to pick? I'll pick this one as my best bet for that sample. What about the next step in the process? Well, it turns out, again, there are several things you might want to do. One of the things that we might want to do is look at the potential regions of occupancy for a series of samples and overlay them and see what they tell us about that general time of life. And if most of them end up in one area, that might be an argument that that was more likely where the animal was. Another thing that we can do is each one of, remember that, I may not have made this point quite firmly enough, but each bit of powder that we analyzed actually was the source of an oxygen isotope analysis, and then that same vial of powder was used for the strontium isotope analysis. There is no worry that you get oxygen from one time of year or place and strontium from another. No, they came from the same mill path. And so we're interested to know where on the range of fluctuating values of isotopes was the sample that gave us a certain strontium isotope ratio, because it's the oxygen isotope ratios that give you the season, so we can tell when it was that the animal occupied a certain bit of the landscape. So now we know where the animal is at a certain time of year. And then here is where we are to go here. This was our Markov model that basically looks at where the animal was in the last time step, where are the possibilities it could be in the next time step. We can rank them in terms of probability by how far they are from one another and how closely they match. And basically you run this model and you run it multiple times and you sort of learn about its behavior, and then you start to generalize about the output. It sounds complicated, it is complicated. I respect the people who do this every day, but it's a wild picture that emerges. Here then is our oxygen isotope data. Here is the strontium isotope data, and you can look at these sort of, I mean, here's the strontium isotope ratio axis here. What is this first little bit of the adolescent life? It's da 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 da. It's monotonous. He's going nowhere. He literally is going nowhere. This is the young male just after he's been evicted, and he's not running off over into the next county. He's staying there complaining about being kicked out. And that's basically where he is for most of a year, until he begins to stray a little bit one way or another and find some other strontium values. And it's not until a few years later that he gets to moving around a bit more, you see more variability. In other words, you see in those values, even just looking at the graph, more is happening. And then there's a third phase of the adolescent history that's right here. The adult oxygen picture is as regular as it was in the adolescent. The picture in strontium isotope ratios is highly seasonal, highly cyclical, but in a very, very patterned fashion. It turns out, you see, the alternating gray and white swaths are years, so you have to look within a white swath or a dark swath to see parts of years. It's sort of just before the middle of this year that you get the high red values here. It's just before the middle of this year that you get the high red values here. It's just before the middle of this year that they get the high red. It's at the same time of year, and those red values are coming at the warmest time of year. That's marking the summer, and that's when the animal is going someplace where it's getting those strontium isotope ratios that are higher than anything else that it sees at that time in its life. The parts of the graph down here show the correlations between the strontium values and the z-scores, which mark season. And I see my time is running short. I'm going to step on the gas here. I think we can leave that. Here's where it comes down to maps. These are the juvenile portions of life. Here's that young animal. It doesn't hardly get out of central Indiana in that first phase of its life. It only begins to stray beyond that in that second phase and then in the third. So he's got a progressive increase in the size of his range. But there is never any seasonal pattern to his occupation of landscape. He just goes where he goes. The time of year it is, it's all sort of about the same. And it's all sort of a mixed occupation picture that is occupying this different areas at different seasons. It's only in the adult, and it's only with summer occupancy that you begin to see something really interesting going on with seasons. And what you see is that in non-summer use, he stays in this general area where he was as an adolescent even. But in the summer, he goes to some areas further to the north. And in fact, there are areas that are indicated here in red that are only represented in the summers. And that's a pattern that we've not seen before. And it's in an area close to there. It's where this little cross and the arrow down to it goes. That's where the dead animal was found. And what time of year did he die? Remember that it was on the upswing of the oxygen isotope ratio. So it was in the summer. So this is all making sense. Here's the cumulative distance traveled by our juvenile. The breadth of this gray bar is uncertainty. Could be this, could be that, but clearly there's not as much cumulative distance traveled as in the adult years, even though it was a shorter span of time. And in the adult here, we've got going on 1,500 kilometers that the animal moves across. Okay. This just shows that it is only in the adult and only near the fossil location where we have this predominant summer occupation. So something was happening that was of interest to this animal, that was associated with his death, and that brought him to that area. So what was it? I want to now come back, we're close to the end, come back to this part of the tusk and these pits that were represented here. That is the cementum defects. You can see them on the actual specimen here. Here's the year boundary, which is a topographic feature, one of these periradicular bands here. And just to the side of it are these cementum defects here. Here's another year boundary. And here I think you can see light coming into these pits. And here's another batch of them. There's two batches right here. They're in the same position relative to winter-spring boundaries. So what are they? This is another mastodon, another tusk, a cast. But what's different here is that you're looking directly at the underside of the tusk. And this is an arc of cementum defects right there. Well, let me go back and see if okay. Here's cementum defects there, here, just a short little arc there, and here, and here, and here. And now I'll highlight those for you. The reason I wanted to show you this is seeing them from both sides, you see, well, some are long and some are short, but look, they're all centered on the same trajectory down the midline of the underside of the tusk. What they represent is damage to the tusk that was highly constrained, and that's my effort to sort of be vague about it for the moment. But here I want to indicate that the corrugation that you see on here has a seasonal signal to it, and all of these occur in, this is the winter-spring boundary right here, and it's just after that that you find the pits, and that was the same story on Buesching. What we're going to see here, this is a digital skull, and this is going to, when I start the animation, it's going to wheel around, and you're going to see a cutaway view of the right tusk, and you're going to see what happens when the tusk is deflected by a downward force on its tip. So it swings around. Here's the cutaway view. Here's the downward force, and here's the rocking action. It rotates about a fulcrum that's up here where the tusk is stabilized within its socket. But the bottom edge of the tusk, the growing edge of the tusk, is forced backward into the bone, and it crunches against the bone at the back of the socket. And that damages the newly differentiated cells that are located right there. This is a cementum defect that's already formed and is now sort of upstream from the growing edge of the tusk. You can see, and here's a longitudinal cross-section, that it's all sort of gnarly structured in this area, but there's definitely a pitting that's evident there at the surface. And in the dentin, there's this so-called sclerotic dentin that's anomalous. Now, the reason that these things caught my interest is that, remember, here's the boundary between cementum and dentin. Dentin is being added in this direction. Cementum is being added in this direction. When cementum is added, it covers over like a blanket of snow. All those ridges, they disappear under those ridges. Why do these pits not disappear? How is it even possible that they remain visible at the surface of the cementum? It's because the cells that make the cementum in that location were injured by being crunched into the bone when the tusk was displaced in this way, and they forever after make sort of gnarly, disorganized cementum that propagates this defect, this signature of trauma, all the way up to the surface, even as additional layers of cementum are being added. So it's visible today, even though it formed years before. And that's what we're seeing on the flank of the tusk. This is sort of a schematic diagram of the back of the tusk socket. You have to understand that tusks are not firmly lodged within their sockets. They're suspended by a ligament, the periodontal ligament, that is sort of stretchy, and they sort of bounce there, and they can be displaced. And what's happening is they are being displaced to crunch this part of the growing edge back into this bone, and that then injures the newly developing cells so that they make this anomalous material ever thereafter. Now, another thing that we're going to see, we're going to in a moment look back at the proximal part of that tusk. There's another kind of breakage that occurs. And it happens, I think, when the tusk, remember this, before we were talking about cementum defects, when something pressed down on the tusk tip. What if somebody came along and crashed into the front of the tusk tip? It would bend it backwards. It would actually, if I go this way, I can imagine it happening on the other side of the tusk. This would be forced into the back of the wall and sort of cut and lodge there, and then the tusk would be bent upward, and you would basically fracture it. And we have examples of a fracture that's propagated up toward the tip from the place where it initiated, and that is what you see here. This fracture is the line that you see here. And this offset that you see right here and that runs up here is a fracture in the living tusk deep within the socket. And when I saw that, I thought, how could that even happen? And at first I thought, oh, it's postmortem, right? But no, it's solid in through there. And when I put my hand inside the pulp cavity, in fact, the pulp tissue must have healed and began to deposit continuous dentin over that fracture. So the tusk, almost to the extent that a tusk can, grew back together over that. But think about what this means. It means that this animal was charging into other animals, thrashing at them this way, thrashing at them that way, uppercut here, uppercut there. The other one whacked at it and tusked it backward in a way that produced a fracture that propagated up the tusk, that tore the base of the underside of the tusk away from the periodontal ligament that surrounded the tusk and produced these periodontal pockets, which are these areas here. My wife has a little bit of this going on in one of her teeth, and she can understand what this feels like. But this is direct trauma produced by fighting animals, going at it like this. This was what they gave one another and took from one another, and the only way to really understand that is it's the trauma of battle for reproductive access. Now, I have gone on too long. I'm sorry. I know that we didn't start exactly on time, but I'm going to let you. The conclusions in yellow here are really just a restatement of what we learned before, the characteristic pattern of the early years of the animal's life, just after age 12 or tusk year 9. What we see in his mid-20s when he starts these battles that are then recorded by all these cementum defects and then tusk fractures. This is the first demonstration of annual migration motivated clearly by mating opportunities that anybody's ever come up with in the fossil record. So it's an interesting piece of history. It's an interesting insight into the biology of these animals. And we have answered our questions that we had there at the beginning. These musk battles became increasingly violent and eventually led to the death of this animal. And we have this isn't a unique case, we've got numbers of animals that show a similar story. For the conclusions in blue down there, I think you get a more sort of philosophical, if you will, perspective on the kinds of things that we're doing here. We're looking at the problems that the animals face and the things that they have to respond to in order to survive, in order to persist. The life history information that we are interested in as ecologists and evolutionary biologists is there for us. It's written in the language of the tusk, which is structure and composition. These are complex structures, and they seem to challenge our understanding at the beginning. But the point is that we can gain insight into them if we are willing to learn more about the processes by which they form. And then the last point is really just to generalize that. The history of the world around us is important, but it is accessible if we're able to engage in deep interrogation of the processes responsible for the Earth and its workings. And at least in my experience, the real motivation for something like that deep interrogation, is ultimately a love of the world around us and of all the living beings that we share it with. And that's what I hope you will take away from this. Thank you. Now I know we have people ready for questions, and you have another one in me, so.
I just want to remind people that we're going to have these mic runners here in the room, and to please put your hand up and they'll bring the mic to you. Please use it so everyone else can hear. We also have people on the live stream. You can enter your questions online. There's a link below the screen that will enable you to type in a question, and one of our staff will help us convey those questions. So here you go.
Do elephants today have the same physiology as the tusks on the mastodons and mammoths?
Right. I've been asked, just so you know, to repeat the questions or paraphrase them at least. And maybe that'll help everybody get. I think those of us in here can hear just fine. Do elephants today have the same physiology that we've recognized in the fossil material here? Largely, yes. The general pattern and type of growth and compositions and so forth, yeah, it's all there. And there were times in this work when I certainly had a reviewer tell me, you cannot talk about must in mastodons because you don't have a must gland preserved, and you don't have this, and you don't have that. How do you know? Well, I don't know, but I see these patterns that match. So what we see in the living animals, it's a hypothesis. It's there for testing. We will gather more data. We will know more eventually. And let me just, I don't want to be too sort of teasing to you, but I need to both maintain some confidentiality, but give you maybe just a peek under sort of a preview of coming attractions, if you will. I guess I didn't give my acknowledgments yet. Here's my acknowledgments. One of the things I'll acknowledge is the M³ program. And we've done some work that's going to have some really mind-boggling results that I hope will be out in a matter of months. So stay tuned, I guess, be forewarned. And I think we'll have an even better answer to your question when that gets out. But we are doing our best to learn everything we can about the animals. It was only because I knew I was running so long that I didn't even touch the slide advance for the next slide. I'm sorry I didn't put this up there at the beginning, but obviously I'm trying to express upon you the importance of these collaborations with individuals, with landowners, with volunteers, with students, funding agencies. All of this is absolutely critical to the work that we do. That's my own addition to your answer to your question. Another one. We've got some up front, and in the middle we've got one back here. Okay, go for it.
Hello.
I can hear.
I live near Saline, Michigan. And I was actually wondering, because I have an interest in extinct animals, more so in the last 500 years, but in general, if the Brennan footprint site was a place that could be visited.
It can be visited, but probably not much seen just now. The site was the place where the trackway is and was actually below the water table. We had to maintain pumps going 24 hours a day, or else catch up the next day if we let them run out of gas. And so we kept it accessible for months. But eventually, the Brennan family decided that we need a longer-term solution, and we decided that the best thing to do was we had documented in every way we could think of. We did major different runs of photography. We did 3D mapping. We did lots of stuff. I'll just say, we then covered it with plastic sheeting, covered it with heavier tarps, and reburied it we put on some large boulders and so forth, and reburied it in sediment from the site. And so it is now a long island, if you will, that stands above the water level in the pond that was left where Harry Brennan had been doing some of his excavation for sediment.
Thank you.
Yes.
We have a question from our online audience. This question is from Olivia. She's in Temperance, Michigan, age 8. We are a huge fan of the documentary Lost Beasts of the Ice Age. It's so cool to see our very own Michigander in Siberia. What was this like, and what was your favorite part of discovering the mastodon?
The trip to Siberia was the favorite part of trips to Siberia, or discovering this of the video. If the question is about the work in Siberia, yes, that's been something that I've been involved in for over 20 years now. It's been extremely exciting. both what we found and living with indigenous people in the far north to see how they found things. Favorite part, I mean, riding Santa Claus fashion, dare I say, in a sled pulled by reindeer, flying into the ground over ridges and so forth, across the landscape, out to the place where the specimen was found. This is baby mammoth. It was very exciting, and just being with these folks who live herding reindeer and surviving today much the way they have for centuries. I actually made observations and learned things that I think have a bearing on mammoth subsistence, because I know the landscape now. I know where the vegetation is. I know what happens when it snows. I know there's just a lot that you learn from being there that you could never get otherwise. Again, a great gratitude to the people and the places and the collaborators.
At approximately age 35 when it died, was this a mastodon in its prime, past its prime? How long did these things live?
We have found them living up into their 60s and 70s, and elephants do the same. I would say this animal was in his prime, not past his prime, but what's remarkable, I think, is just how vigorous, how sort of all in they are. What does it take to survive? What does it take to adapt? It takes successful reproduction. What does that take? The odds are high. They give it everything they have, and sometimes it's an early end.
What percentage of male mastodons do you think died as a consequence of injuries incurred in these kinds of battles?
Right.
Yeah.
I would say we always want bigger samples, but I would say with what we have, we could say that maybe 10 to 15% of males might end that way. Okay. Which, is that a big number or is it a small number? It's kind of a big number. It's certainly not the only thing they face as a threat, but it's a major factor in their ecology. And it probably explains why their bones are several times more massive and heavier than the bones of similar-sized elephants. Elephants actually have bones that are quite slender by comparison. Mastodon bones are like this. Just right here in the front row. Oh, okay. Yeah.
How you tell lives in a mastodon's tusk? Is that like to finding lives in a tree stump?
Yes, it's very much like it. Lines, I think we're talking about. How do you interpret the lines, the layers in a mastodon tusk, and is it like trees? It's very much like trees. A difference is that trees grow from the inside out. So when you cut across a tree, the remote past is in the center of the tree, and the recent years are toward the outside. Tusk is just the opposite. And you think, oh, how can it grow from the outside in? Well, it's this stack of cones. Because if you cut across the stack of cones at any one place, the oldest ones are on the outside, and the most recently added ones are on the inside. So it's a good observation.
How about how long are the tusks?
How long are their tusks?
Yeah.
The tusks, this animal, were right about 3 meters long, so that's 9 feet and a bit. This is about 6 feet, so half again as long as that. It would take two of us to sort of reach from one end to the
We have another question from our online audience. Can you tell anything about the mastodon's diet from your studies?
Not from this study, but from others. Had we been doing our analyses for oxygen on the oxygen out of the carbonate component of the mineral hydroxyapatite, that's also there, you would get both oxygen isotope information and carbon isotope information, like almost for the same analysis. It's a little bit more complicated, but the bottom line is that would have told us, it at least would have allowed us to say, was it more this kind of food or that kind of food? We would, not an absolute menu, if you will, but quite a bit of information can come from carbon isotopes. There are also nitrogen isotopes that we look at, and that tells us a lot about both what they're eating and also the condition of the animal, whether it's starving and sort of metabolizing some of its own tissues or not. And then we've had a couple of chances where we really hit it in a good way, where we found actual intestinal tracts, partial intestinal tracts. Even sometimes the tissue of the intestinal wall itself was decomposed, but only after it was buried in dense sediment. And so that we have a cylinder of material that was intestinal contents sort of there within the sediment package in which it was buried. And we've sampled that, and we've actually cultured that material for microbes and have revived what evidently were living intestinal microbiota of Pleistocene herbivores. I mean, in other words, the animal died, it was buried, but its gut microfauna was still sort of hanging on, waiting for times to get better again. So in those cases, we had lots of information. We can do microscopy, we can look at pollen, we can look at plant tissues, cuticles and things like that, and tell really what it had for that meal. Also in our baby mammoths, we had curdled remains of her mother's milk in her own stomach and intestine. So, and she was of an age, it was a month old when she died, so she was absolutely nursing at the time of death. And there's a chemical signature for nursing as well. So many of these kinds of things, yes, there are answers if only we dig enough.
We have a question over here.
What is the key differences between mammoth species and mastodon species?
Key difference between mammoth and mastodon species. If you mean a key trait that will distinguish them, probably the easiest way to do that is to look at their cheek teeth, as we call them, their molars and so forth. And mastodons have these rather high cusps. You can see them on the exhibit. We have a mastodon tooth that you can touch and a mammoth tooth. Mammoth tooth looks more like sort of the sole of your shoe, some shoes. It has these parallel ridges of enamel and dentin and so forth that are exposed as part of the chewing surface of the teeth to help break down the plant material that the animal ingests. So in each case, the species, biological species are biological species, they have sort of some of the same biology, some of the same mating patterns, and some of the same patterns of longevity and so forth. But all species then have these different traits by which we can learn to recognize them, and which are what, after all, evolve over time and give rise to some of the diversity that we see in the world. So these are all problems are kind of related when you get to looking at it.
This is an interesting question. Have you done any work with the folks in the College of Dentistry? It seems like there might be some overlap there.
There certainly could be, and I have done some work with people in dentistry. Not as much as I would have liked to. It's just, what can you do? But absolutely. Well, I can get more specific than that. I mentioned Adam Roundtree, and he was doing some of his work on a problem in tooth development, and it was people in dental anatomy and so forth that were interested in the solutions of that problem. I won't go into all the details there, but absolutely the kinds of things that we study are general questions that have applications beyond paleontology. We humans are kind of animal, and the sort of developmental problems that we experience are not so different from problems that other animals have. So the more we learn about all of these, I think the better off we all are.
I believe that there was a low growth here in the Buesching mammoth's 20s, and I wondered if you saw any skeletal damage or any other healed damage that might explain why he had a low growth here.
If you mean that time when the line went way down there, I've looked at that and tried to figure out. It's not quite clear what was happening. A lot could have healed and not be recognizable today, after 8 years, something like that. So I don't think I have a good answer for that yet, but there are times when we can absolutely answer questions like that. There are other animals that we've studied where we see this that happened right before death, this that happened probably a year before that, this that happened 2 to 3 years before that, and so on. Our bodies are their own kind of records of our hard times. So
I think we'll have one last question from our online audience because it's getting so late.
Okay.
Okay. This question is specifically about the cementum bands. While I understand why annual and seasonal and possibly lunar cycles would be visible, is there a good explanation for why cycles such as weeks would show up in a biological system?
This is about the cycles that are on the order of weeks in duration within a biological system. This is one that I have worked on for years now, and has puzzled me for years, but I have given other talks where this was one of the main issues. And I do have a model that I believe explains it, but I lack at the moment all of the experimental sort of validation and clarification that would let me flesh out all the details of the model. So it's not a finished piece of work. And I guess there isn't probably a simple answer, but let me try to go at least a couple steps toward an answer. But again, this is the way a lot of science is. You don't have it all yet. It's for the next generation maybe to find out. So what's my first steps? I think it's a consequence of an interaction between a circadian rhythm, which everybody knows you may have circadian rhythms in body temperature and production of certain hormones, and we have this 24-hour-a-day cycle that our bodies go through, and we know when it's time to get up, when it's time to do different things, and a lot of physiological processes sort of follow sort of the timing that seems to be demanded by this circadian rhythm. But circadian rhythms are essentially always, almost by definition, actually an expression of an intrinsic rhythm that is not exactly 24 hours in periodicity. It's something else. It's like 24 3/4 or something like that. And what happens in our body use of the rhythm is it continually resets where we are in the cycle in response to a daily cue, often a cue of exposure to light. You say, oh, it's not exactly that time. Oh, no, okay, I'll just adjust my watch a little bit, and I'll be good. I'm good to go. So we keep resetting, and that, of course, is how we recover from jet lag. And so we have these rhythms. But what leads to a week? My model shows how there can be a circadian rhythm that interacts with another non-circadian rhythm, and the two rhythms develop a sort of a pulse. We actually use this in tuning instruments often. There's a periodic enhancement of a change in tone. I have done this with an example, a sort of demonstration with two tuning forks that aren't precisely the same. Both sound like a clear tone, but if they're not the same, you strike them together and go, oh, 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 oh. There's a modulation. You use that to tune your instrument. You want an exact, say, C on a certain string, take the C tuning fork, and if it sounds a clear tone, you're good. But if you may have to tighten the string or loosen the string in order to get rid of that modulation, and it will gradually disappear as you bring them into precise same frequency. And I have some ideas about what the non-circadian rhythm is, but not real empirical evidence for it yet. But I can tell you that I can easily calculate for you what the periodicities have to be for what's called the beat frequency. That's this modulated thing that I was, for the beat frequency to be a beat frequency of 1 week. And it's not far off of the circadian rhythm. So I just have to find the process and measure its periodicity, and we'll have something that produces a week. If this is in fact what's going on. So that's to be continued, I guess.
Please join me in thanking Dan Fisher for a wonderful talk this evening.